everyone. Today I'm really excited to share my recent published research paper titled Forecasting Daily Customers Flow in a Restaurant, a multi-factor machine learning approach. So, this paper explores how we can predict customer foot traffic in a restaurant using various machine learning algorithms, techniques. It was just published in August 2025, and I am really proud of my work. In this video, I will give you an overview of the paper, including the problem we addressed, the data we collected, and the method we used. So stay tuned for more details. Yes, so let's begin from the abstract of the paper. The paper presents a case study on predicting daily customer flow in a restaurant, a critical area for the service industry. We conducted a systematic analysis of multiple machine learning algorithms, including XGBoost, random forest, LSTM, and linear regression. There were four models we compare with each other. And then we use different combinations of the feature from different categories of time series analysis features formations. So those features include internal and external features. We use around 52 different features and tested them on all individual algorithms. Idea was to find optimal algorithms and optimal feature set that we can apply in our restaurant. So we tested from M1 to M10, giving them the name baseline and with including category by category features. We evaluate our model using MAE and MSE, RMSE. And we observed that pre-processing was important during our applications. So pre-processing gave us an idea why there was a leak in between the data. So there was a COVID time. That's why we need to remove the data because that data was missing. Our findings suggest that XGBoost outperform other algorithms using MAE, RMSE, and the MSE models. After discussing detail about abstract, let's move to the introductory part and problem statement of the paper. So this case study introduces an approach for predicting daily customers demand in a restaurant using daily data and its advanced machine learning methods. So after COVID pandemic, restaurants located in a different offices experience a reduction of up to 30% of average number of customers due to the rise in the amount of remote work. Now, what is problem statement of the paper? What we are going to address? Basically, restaurant struggles to accurately predict how many customers they will have each day and how many of them will visit them, especially with the recent changes like more people working remotely. This makes it hard to manage food, staff, and overall of operation efficiently. The problem is to find best way to forecast daily customers numbers in a restaurant so it can better manage and reduce the food waste. Abstract. Now let's move towards introduction and the methodology part of the paper. In the methodology part or method part, prediction method part, we have a workflow architecture. So workflow of the customer prediction model. So let's discuss this workflow overall model for the predicting customer data. Overall model looks like a complete cycle here. So we have Filaveria data as an input and customer prediction is output. You can see on top and bottom. Then first step, which is a very critical step, is a pre-processing step of the data. During pre-process step, we perform three different operation, including data scaling, filling missing data, or removing null values. These pre-processing steps are making data ready for the further step like a feature formation. This is critical step because we remove null values and remove gaps if the data is missing somewhere, and we just exclude the corrupted data, like data scaling. Then we have feature formation, which is a combination of different categories of feature. We have six different categories of features. For example, we have a temporal baseline features, we have external feature or weather features, and we have events like holidays, day before holiday, day after holidays. We know there's a holiday. If somebody has holiday and the next day or day before, people normally make holidays themselves. So these are critical features, and we try to analyze the effects of the holidays and day before and day after on the data. And then we have statistical features like rolling mean, exponential smoothing, and autocorrelation. We found one problem that data leakage also. So because the data was stealing the future data, so we need to shift plus one a day to avoid the data leakage. Then we have other features, which is very critical feature, which is a previous day customers. So data has a pattern, trend, and relationships with the previous day customers. And finally, we have a menu features. Menu features include vegetarian, if there were vegetarian food served on that day or not, true false boolean features. Then we have a meat, and then lactose, and then gluten. In Finland, lactose and glutens are highly important features. After the feature formation section, we need to select the features. Feature selection. Feature selection has M10 different categories. Like from feature formation, it was making a feature taste, like we just named them M1, M2, M3, M10. So M1 we picked base features or temporal feature, and on top of that we were adding other feature. For example, M1 plus weather feature becomes M2, and then we have M9 menu plus M1 becomes the M9 feature, and M10 was the optimal features or the best features according to the score or the MAE score that were they were getting with the best feature performance score. So our idea was to test most of the feature in order to find optimal M10 based features from different categories. There were like 52 different features. After feature selection, we have model training and testing. We use 80 by 20 model training and testing. So we test four different time series forecasting models. We use XGBoost, random forest, LSTM, and linear regressions. We test although other two models also profit and one other model, but their result was not good, so we didn't include in the paper. So finally, the best model was XGBoost. XGBoost outperform all other models. So we select XGBoost and based from all features, and then we have predict future values. Next, after workflow architecture, we have two figures to discuss. One is like how data looks like, and the second figure is about how many customers visiting a particular time or peak hours. So let's discuss both of these figures individually. We have data collected from 2019 to 2024. In a figure graph, we have on x-axis we have unique customers, and on y-axis we have year or date. So this is like a time series data. In time series data, time stamp data is important. So we had initially data in sessions, in hours, how many visitors, customers visiting our restaurants. So we just combine the data into days. So big dip during during anomalies detection. So we just set 50 as a lowest threshold, and we had around mean average plus 100 customers as a maximum threshold. We found that there was a dip between 2020 and 2021 because of the pandemic. So in order to perform well, in order to predict well our model, we remove that dip pandemic data points from our system. Next figure shows the customers' peak hours in a restaurant. So we figure out that the time between 10 to 11, there were like 48 percentage of the customers in that particular time. So this help us to find busiest hours for the restaurant and food demand. Okay, after hours of the day, let's move to the table 3 and table 4. Two important table within a paper, table 3 and table 4. So table 3 represents data overview, which is from 2019 to 2024. And other table is about temporal features, which are derived from the time column. So first we discuss about the data overview. The original data set was 1,881,870 rows. After filtering, means removing the COVID time, pandemic time data, we got 1,347,356 rows. So you can see the drastic change. Then we have temporal features. Temporal features derived from the time column. So year from the year, month, and then we have a day. Then day of the week, which 0 is Monday, and 6 is like Sunday. So each numeric value represent the day of the week. Here we discuss table 5, example of statistical features computation. So how these features computed. So we have customers, and these all three features are computed using customers using formula. So rolling means, exponential smoothing, and autocorrelation. All of three features have their own formula. Based on the customers, they calculate according to the formula. Now here in table 6, we see the most important feature for predicting daily customers flow. The The biggest factor is the number of customers from previous day with a very high importance of 65.5 percentage. This shows that yesterday's customer count strongly influenced today's data because it reflects the latest trend and quick changes like promotion or events. The next important feature is exponential smoothing at 9.2 percentage. This feature helps and capture recent patterns while smoothing out random ups and downs. Our third important feature is a holiday with 6.1. Since holiday usually causes big jumps or drops in customer numbers, we also see rolling averages, the day 5 rolling mean at 5.2 and 30-day rolling mean at 2.5. So these help us to understand short-term and long-term patterns in our customer flow. The features like air pressure, week of the year, wind direction, and day of the week have much smaller effects, each below 2%. So our recent number of short and trend matters the most, while weather and calendar details play only smaller role. So overall, table 6 provide the feature importance, and we select top 5 features for M10. Okay, next we discuss about the figure 4, which shows how a data looks like complete features with their values. So this is the toy example of the data with all different 6 categories of features. So we covered baseline, weather, event, statistical menu, and then we have other features like a previous day and so on. The critical and final section of the paper is result section, which evaluates the performance of 4 machine learning models: XGBoost, random forest, linear regression, and LSTM. We use 4 evaluations matrices: RMSE, MAE, and MSE. So we avoid MAPE, which can be unstable to zero values. In our data, holidays, and sometimes there are data missing, so it will be unstable and suggest MAPE. We suggest for future value work focusing on MSE. So what is RMSE? First of all, RMSE stands for root mean square error. MAE, second number evaluation matrices, mean absolute error, and MSE, mean squared error, are common matrices used to evaluate the performances of our models. These measures they measure differences between predicted and actual values. So we have predicted value, and then we have the actual values they compare. So RMSE overall gives greater weight to large error values, while ME represents average absolute error. MSE is simple square average of the errors. So RMSE is under a square, under root, and MSE is a square, basically. So the choice of matrix wholly solely depend on a specific problem and emphasizes on penalizing large errors. So in next few slides, we will discuss results from each matrices individually with a figure and bar chart. So let's start from the RMSE table 9 first. It is impressive performance of XGBoost model, which achieved the lowest RMSE in this study. As seen in table 9, the XGBoost model outperformed other 3 models like LSTM, random forest, and linear regression. This is also reflected in the bar graph, where the XGBoost bar, colored orange, is clearly shortest, indicating the lowest RMSE score of 111 compared to the others. So these findings suggest it is the most effective method for this particular task, providing superior predictive power compared to the other evaluated models. The random forest on second number also showed competitive performance, though not quite as strong XGBoost. In contrast, the linear regressions model had the highest RMSE, indicated it was less suitable for this specific data set. Now let's move to the MAE. Next, we examine the mean absolute error or MAE. Table 10 presents the MAE values for different models and feature sets. Consistent with the RMSE result, the model achieves the lowest MAE across different feature sets with an average MAE of 76. Same you can see on graphical bar. So let's move to the MSE now. Now let's dive into the MSE, mean square error. Table 11 shows the four models performances using MSE. So we can also see the graph bar chart that represent the same result. So we can clearly see XGBoost overall dominates three of these matrices. So here in MSE is 12,354, lowest than any of other model in M10 with the best features. And on average, it is 13,712. So let's move to the next slide. You can see here the figure with the actual customers with the XGBoost predicted values. You can see predicted values with the XGBoost orange color follows the patterns and trends is the actual. So it's almost similar. There are like very little zigzags. So overall, our model Boost performs very well. On x-axis we have number of customers, and on y-axis we have year or time. So let's discuss about detail on the results. So overall, we tested how different factors and model can predict daily restaurant visitors, where interestingly, weather variables like air pressure and wind direction had only small impact. This shows why it is important to evaluate each feature carefully before building the model. When we compare model XGBoost outperform all the other models with the lowest um, across all the matrices. It captures complex pattern very well, making it more reliable choice. On the other hand, second one was random forest, who also did reasonable but was slightly less accurate. Third, LSTM, which usually works well for time series data analysis, but underperforms here because the dataset didn't have a strong temporal patterns. Final model was linear regression, while simple, still worked well in certain cases, especially when the data relationships were more linear. These results tells us two important things. One is features models like XGBoost are excellent for complex non-linear data. Second, simpler models like linear regression shouldn't be ignored when the data fits that their assumptions. Beyond these models, we also found features like holidays, day of week, and smoothing method improved prediction accuracy. Although previous day was on top. And most importantly, careful data cleaning and preparing proved just as important as model choice because we filter out the pandemic COVID time data and look. So we add new data sources such as menu details, even building usage data could make prediction even better for the futures. Finally, these models can directly help restaurants weekly forecast support and ordering the next day focus help preparing same day food and forecast the food demand and reduce the waste. So let's move to conclude the paper. Let's conclude the video and paper. Our study compare four different machine learning models: LSTM, XGBoost, random forest, and linear regression for predicting daily customer flow in a university restaurant. The results were very simple and clear, where XGBoost consistently outperformed all other three models. Across all the feature sets, it was especially effective in capturing short-term customer trend, thanks to features like previous day customer, exponential smoothing, and rolling averages. At the same time, we saw the linear regression is still a good choice, with a strong result when data was simpler and more linear, especially with feature set M10. This reminds us that even simple models can be useful when the data matches their strengths. Overall, our recommendation is that operators managers should implement an XGBoost model with a recent historical feature. For those interested in the technical side of this paper, I invite you to watch the next video where I walk through the complete Python implementation step by step. So I have a completely also implement that XGBoost and all those steps in Python program. So please follow that video as well. Thank you for watching and for your time.